Good evening. Welcome to the course on electromagnetic fields. Electromagnetic fields. Let us start our discussion with the syllabus. Here is the syllabus. Topic number 1 is a vector calculus. And coordinate system. Topic number 2 is electrostatics. Topic number 3 is magnetostatics. Topic number 4 is time varying fields. Time varying fields and Maxwell's equations. Time varying fields and Maxwell's equations, 4 topics, a very short subject. Okay, in the GATE exam, it is not fixed. Minimum 2 marks to maximum 6 marks are expected. Okay. And in the engineering service exam, (6% to 10% of the questions will be asked in the prelims as well as the mains. And it is also important in the state services, especially like TS Genco, TS Transco, AP Genco, AP Transco. State services, minimum 4 to maximum 5 questions are expected. State services. Four to 5 questions are expected. Very simple questions are expected from this subject. Okay. This is a syllabus and this is a weightage. It is approximate. It is a rough estimation. It's not fixed. Yes. So this is what notice from your previous papers. It is a survey on your previous papers. Fine. Now, obviously, we need to start with this topic number 1, vector calculus and coordinate system. But before going into the topic number 1, let us have some motivation. Let us start something like this. What is the reason for studying this electromagnetic theory? Or what is the need for studying this electromagnetic theory or EMF or electromagnetic fields or electromagnetic field theory? Different names are there, or simply electromagnetics. Different names for this subject are simply electromagnetic fields, EMF. In short, you can call it as a EMF. Electromagnetic fields. So let us start with some question here. What is the need for going for this electromagnetic theory? What is the importance of this subject? Fine. So here, as you all know, you all are introduced to the world of electrical engineering through the concepts of voltages and currents, isn't it? So when you start studying your electrical engineering, you'll start with the very fundamental subject, what is called as circuit theory. Yes or not? You'll talk about what is called KVL, voltage, current, KVL, KCL, and then Ohm's law. By using these things, you'll study your electronics or electrical engineering or electrical circuits. So that is a very fundamental introduction to your electrical engineering. Now, my question here is that the knowledge of voltage and currents are not enough in understanding the different aspects of electrical engineering? The answer is no. Suppose if you want to understand the different aspects of electrical engineering, for example, if you want to understand the working principle of a transformer, if you want to understand the working principle of a motor or a generator, or if you want to understand how the energy is stored inside the capacitor, or if you want to understand how the magnetic field is stored inside the inductor, or if you want to understand how the energy propagation, EM energy propagation happens over the long length transmission lines. Like this, I can list out so many things. If you want to understand the different aspects of electrical engineering, just by having the knowledge of voltage and current will not going to help us. Let me put it onto the board. I'm going to turn the page here. So what I'm saying here, we are all introduced to the world of electrical engineering or electronics through the concept of what is called a voltage and then current. These are governed by the equations KVL, KCL, Ohm's law. But unfortunately, just voltage, current, KVL, KCL, Ohm's law cannot help us in understanding the different aspects of electrical engineering. Okay, so what we need to do here is we need to go back to the fundamental quantities. What are the fundamental quantities here? The fundamental quantity behind the voltage is the electric field. You need to go back to the fundamental quantities. The fundamental quantity behind the voltage is the electric field. The fundamental quantity behind the current is a magnetic field. Okay, so after entering into the subject, you'll notice that line integral of voltage will give, line integral of electric field will give voltage, and line integral of magnetic field will give current. Or in other words, just remember that the scalar equivalent of electric field is a voltage. The scalar equivalent of magnetic field is a current. Clear? So when you go back to the fundamental quantities, what you will notice here is there exists an interplay or interdependence or coexisting mechanism between both electric and magnetic fields. Electric field will be dependent on magnetic field, and magnetic field is dependent on electric field. I'll repeat again. What is the relation between voltage and current is given by? The relation between voltage and current is given by what is called a Ohm's law. Okay, fine. So here, when you go back to the fundamental quantities, the fundamental between the two fundamental quantity, there exists a interplay or interdependence or coexisting mechanism. Electric field will be dependent on magnetic field. Magnetic field is dependent on electric field. Electric field is dependent on magnetic field, and vice versa. Or in other words, you can also say coexistence. Electric field is due to magnetic field. Magnetic field is due to electric field. Electric field is due to magnetic field, and so on. Interplay, interdependence, or coexisting mechanism between both electric and magnetic fields, which is called EM phenomena. This is called EM phenomena. This is called EM phenomena, interplay, interdependence, or coexisting mechanism. And how this EM phenomena is explained? This EM phenomena is explained with the help of what is called four Maxwell's equations. Four Maxwell's equations. Okay, so why we need to study about this EM phenomena? Yes, because this is a common thread which is running behind in our all electrical engineering aspects. Suppose if you take the uh, working principle of a transformer, that is can be explained by what is called a EM phenomena, some or other form, what is called a Faraday's law. Suppose if you want to know a working principle of a generator, again Faraday's law. If you want to know a working principle of a motor, again there requires what is called a magnetostatics. Magnetostatics is a special case of EM phenomena. Again, if you want to know how the energy is stored in the capacitor, so the energy stored in the capacitor is the electric field, that is electrostatics. Electrostatics is a special case of EM phenomena. And if you want to understand how the what is, if you want to understand the working principle of an inductor, inside the inductor there is a magnetic field. Magnetic field is nothing but a magnetostatics. Magnetostatics is a special case of EM phenomena. If you want to understand how the energy propagation happens on the long length transmission line, again there is a EM phenomena. So the entire electrical engineering, what is a common thread in a different electrical engineering aspects is the EM phenomena. Whatever the thing you take, all the things, all the different aspects runs. The show which is running behind all these things is a EM phenomena. So the EM phenomena is a common thread which is running behind all your electrical engineering aspects. Okay, fine. So, but this EM phenomena, to put it in a simple words, what is the EM phenomena? Change in electric field will give magnetic field. Change in magnetic field will give electric field. That is called EM phenomena. And this that change in giving this one is called a EM phenomena. And EM phenomena is explained with the help of four Maxwell's equations. Clear? Yes. Let me write down these four Maxwell's equations. How do they look like? Just you need to observe them. Maxwell's equations looks like this. The first Maxwell equation is something like this. Del cross H is equal to J plus dou D by dou T. Del cross E is equal to minus dou B by dou T. Divergence of D is equal to rho V. divergence of B is equal to 0. You will get these 4 Maxwell's equations at the end of the lecture. But I have written in the very first lecture itself. I wanted to make some observation here. So these are the Maxwell's equations. Here, J is equal to, we'll talk about all these things later. J is equal to sigma into E, and then D is equal to epsilon into E, B is equal to mu into H. See here, these are called Maxwell's equations. Something like a del cross H is equal to J plus dou D by dou T. Del cross E is equal to minus dou B by dou T. Divergence of D is equal to rho V. Divergence of B is equal to 0. Looking very complicated equations. But see here, in the case of circuit theory, our life was very simple, isn't it? You can use what is called a KVL, KCL. What is a KVL? Algebraic sum of voltage in the loop is equal to 0. What is KCL? Current entering the node is equal to current leaving the node. What is Ohm's law? V is equal to IR. Our life was very simple. Here we are dealing with what is called a vector, and we are dealing with what is called a EM phenomena. And that too here, this curl of curl, all these are something mathematics, isn't it? So you want to understand what is called the EM phenomena. To understand the EM phenomena, you should know what is these 4 Maxwell's equations are. But the Maxwell's equations are in the vector calculus. The language of understanding the Maxwell's equations is the vector calculus. Yes. So ultimately, observe here. Let me go back. That is the reason why your topic number 1 is dedicated for the vector calculus and coordinate system. Okay. Yes. So what we're going to do here in the vector calculus, topic number 1, we're going to discuss all the necessary mathematics required to understand what is called a EM phenomena. Yes, through the Maxwell's equations. Clear? Fine. Let me turn the page here. So far we haven't discussed anything. Just I have given some motivation to the subject. Let me write down something like a points here so that we'll understand. Only the concept of voltage comma current can't explain a different aspects of electrical engineering. What are the different aspects of electrical engineering? Transformer action, comma, motor action, comma, generator action, comma, capacitance, comma, inductance, comma, long length transmission lines, etc. So these are the, if you want to understand all these things, just by having the knowledge of voltage and current will not going to help us. So what you need to do? You need to look back to the fundamental quantities. Here the fundamental quantities are electric field and magnetic field. So the EM phenomena will provide what is called a different ways of explanations and solutions to the different aspects of electrical engineering. Yes, EM phenomena, EM theory. EM theory provides flexible solutions and explanations to the different aspects of electrical engineering. Number 3. Then what is the EM phenomena? To put it in a simple words, EM phenomena explains the interplay or interdependence or coexistence mechanism between both electric and magnetic fields, isn't it? EM theory simple words. EM theory explains the interplay or interdependence or coexisting mechanism between both electric and magnetic fields. EM theory explains the interplay or interdependence or coexisting mechanism between both electric and magnetic fields, which is explained with the help of 4 Maxwell's equations. With the help of 4 Maxwell's equations and script, SCRIPT script, that means language, and the script is written in terms of mathematics. And the script is written in terms of mathematics, in brackets, vector calculus. And the script is written in terms of mathematics, in brackets, vector calculus. So what is the language of understanding electromagnetic theory? Is a vector calculus. The subject is all about EM phenomena. If you want to understand EM phenomena, you should know what is called a Maxwell's equations. So the subject is all about deriving the Maxwell's equations. Deriving the Maxwell's equations, defining the Maxwell's equations, explaining the Maxwell's equations. See, what these equations are, we're going to derive later. Just I wanted to observe what is the first equation is saying, second, third, fourth, what all these things we're going to discuss anyhow in our subject. Just I wanted to show here that there exists something like a 4 Maxwell's equations, which explain what is called a EM phenomena. So the EM phenomena is a very important thing in our electrical engineering. That is what we're going to do. That is what we're going to study. Just it is a motivation. That's it. Fine. Now let us start formally with our topic number 1. Vector calculus and coordinate system. Clear? Yes. I'm going to turn the page here. We're going to start formally with our topic number 1. Vector calculus and coordinate system. Vector calculus and coordinate system. Yes. Okay, let us start with the definition of the field. Let us start with the definition of field. Okay. So how later we're going to use extensively the word what is called electric field, magnetic field. So we should know what actually the field is. Okay. Let me write down the definition here. Field is a physical quantity. Field is a physical quantity which takes different values at different locations. Field is a physical quantity which takes different values at different locations. What does that mean? Suppose let us take the temperature. How do you convey the temperature in general? You will convey the temperature in the average sense. 22 degrees, 24 degrees, 30 degrees, isn't it? But strictly speaking, is that the temperature is same everywhere in the room? No. In the hall, it is different. In the kitchen, it is different. At the different points, it is different, isn't it? So, observe the read the statement what I have given. Field is a physical quantity, something like a temperature. Okay, it is something like a temperature. It is different at the different locations. So you can say that in the hall it is some 22 degrees. Near the AC it is different. In the kitchen it is different. So at the different places in the room it is different. Then you can say that your room is in the temperature field. Which field is that? Temperature field, isn't it? So physical quantity which is taking different values at different locations. Then you can say that your room is in the temperature field, certain region. Okay, let us take some other example here. Example number 1. Let us take the earth surface. Suppose if I am holding this mass, I am experiencing the force. The force experienced by this mass is different at the different locations, isn't it? Generally, strictly speaking, at the poles it is different. At the equator it is different. So at the different points on the earth surface, the gravitational force is different. Yes. So here it is. Earth surface. Suppose if I am holding some mass here, the force will be pointing towards the center like this, and the force value is F1. If I am holding some mass here, the force will be towards like this. Here it is F2. Here it is F3. So at the different points on the earth surface, the gravitational force experienced is different, isn't it? So what is the physical quantity here? Gravitational force is a physical quantity. Yes, then you can say that earth is surrounded by gravitational field lines. Okay, let me turn the page here. Let me give one more example. Example number 2. Let us consider the charge Q. From your basic physics, you know that if I bring other charge near to that one, what happens? It will going to experience the force. Later we will going to see with the help of what is called a Coulomb's law. What is the nature of that force? What is the expression? We will going to see later. If I bring the same charge in other direction, it will going to experience the force F2. And here is a charge Q. Here it is F3. Here is a charge Q. Here it is some F4. So at the different points around the charge Q, the force experienced is different. Then you can say that charge is surrounded by what is called electric field lines. Let us take one more example. Example number 3. Let us consider the current carrying conductor. It is carrying the current I0 and length of this one is DL0. I will bring the other current carrying conductor near to this one. Here it is I DL. So if I bring the one current carrying conductor near to the other current carrying conductor, it will going to experience the force. What is the nature of the force? That we going to study in the magnetostatics. Just a simple observation. Here it is F1. If I bring the same current element in other direction, it will going to experience some F2. If I bring the same current element in other direction, here it is F3. Here it is IDL. F4. That means if you have a current carrying conductor, if I bring the other current carrying conductor at the different points, force experienced is different. Read the statement what I have given. Field is a physical quantity which takes different values at the different locations. What is the physical quantity here? F1 here, F2 here, F3 here, F4 here. What is the physical quantity here? Magnetic force is a physical quantity which is different at the different locations. Then you can say that this current carrying conductor is surrounded by the what is called a magnetic field. What it is? Magnetic field. Here there is a charge here. At the different points, the force experienced is different. F1 here, F2 here, F3 here, F4 here, and so on. Isn't it? So at the different points, the force experienced is different. Then you can say that this charge is surrounded by what is called an electric field. Let me go back. Here is a earth surface here. If I bring some object here, this is any well-known example for us. At the different points, the force experienced is different. Then you can say that earth is surrounded by what is called gravitational field. What it is? Gravitational field. Read that statement what I have given. Field is a physical quantity which takes different values at the different locations. Clear? Fine. So what are the some of the examples for the, there are two types of fields. One is a electric field, other one is one is a vector field, other one is a scalar field. I will not go into the definitions. What is a vector field? At each and every point it will have a direction as well as a magnitude. What is a scalar field? Scalar field only magnitude, no direction. Clear? Yes? Fine. Now observe here carefully. What are the examples of the vector fields can be given? I will directly go to the examples. Examples of vector fields. Examples of vector field. What is the first example here? What are the examples of the vector field? Water flow in the river is the best example for the vector field. At each and every point, it has got a direction as well as the water is moving with certain velocity. Water flow in the river. Number 2, air distribution around the fan. What is the air distribution around the fan? At each and suppose if I am just below the fan, if the air is moving with certain velocity and it is circulating, and if I go away from this one, the velocity decreases. So air distribution. Air distribution around the fan. Number 3, electric field, magnetic field, anyhow vector fields that I will going to justify later. Electric field. Number 4, magnetic field. Number 5, if you want gravitational field. Okay. Yes. Yes. Now observe here. Then what are the examples of scalar fields? Examples of scalar fields. Number 1, temperature, isn't it? Temperature distribution, how the temperature is distributed in our living room, or how the temperature is distributed in the mountain region, whatever it may be. Number 2, electrostatic potential, or it is popularly known as voltage in our circuit theory. Yes. So electrostatic potential, or simply it is called voltage. If the electrostatic potential is constant, then it is called voltage. We'll learn anyhow later. See, let us focus on these first two examples. I've intentionally, purposefully, I've given these two examples. Water flow in the river, air distribution around the fan. We haven't discussed about electric field. Now, what is the nature of them? That we're going to discuss anyhow later. Anyhow, you have some basic idea about water flow in the river. In general, what is the water flow in the river? It is a straightforward field. Yes or not? Here is a water flow in the river. This happens like this. What is the air distribution around the fan? Circulating. So by taking these two examples, what I wanted to show? I wanted to show here that there are different types of natures of fields are possible. Some fields may be straightforward in nature. Isn't it? Water flow in the river is a straightforward in nature. Air distribution around the fan is a circulating in nature. So here what I want to convey by taking these two examples is I want to show here that I want you to visualize that there are different types of fields are possible. Some fields may be straightforward in nature, some fields may be circulating in nature, or some fields may be general. It is a combination of both straightforward as well as circulating. Clear? Yes. I'm going to turn the page here. Now I want to write what is called attributes of fields. Attributes of field. What is this one? Number 1, number 2, number 3. What is the meaning of attributes of field? Suppose if you take the human body, there are some attributes. There is some height, there is some weight, there is some color, isn't it? Suppose if you take some chair, what you sit on, it will have some height, some width, some height, some volume, some mass, some color, isn't it? Similarly, how you can describe the field? Field will have some magnitude, isn't it? It will have some magnitude. Suppose let us say the water is moving from this, falling from this much height, will fall with certain force. If it is falling from this much height, it will going to fall with a very stronger force. The electric field, for example, the electric field which is coming from the 1 microcoulomb of charge is something. If it is coming from the 10 microcoulomb charge, it is very strong. So the field will have a magnitude. Number two, field will have some nature. Some fields may be straightforward in nature. Some fields may be circulating in nature. Some fields may be combination of both straightforward and circulating. Number three, uniqueness. What is the meaning of uniqueness? Each field is unique by itself. Suppose let us take, there is a magnetic field which is coming from 1 ampere of current carrying conductor, and there is a magnetic field which is coming from 10 amperes of current carrying conductor. So the magnetic field which is coming from the 1 ampere and 10 ampere will be different. What is the unique for the human beings? Fingerprints, isn't it? Fingerprints are unique. In a similar way, the behavior of the fields are unique by itself. What does that mean? We're going to discuss later. So if you want to know the fields, you should know these three things. Magnitude, nature, and then uniqueness. These three things can be done with the help of what is called a vector calculus. What is the vector calculus here? The vector calculus operators will going to measure the magnitude and capture the nature, and it will going to define them uniquely. Okay, let me write down what we're going to do. Remember, it is not a mathematical definition of the vector calculus. Here we are going to discuss the vector calculus according to our subject requirement. You would have already learned this vector calculus in your mathematics, but here our discussion will be more of physical interpretation. So in a mathematician like it to be defining in a more mathematical format. You're going to give some formula, you're going to solve some questions here. Our interest is more on the physical interpretation of each and every operator. Okay. So I'll give the definition also same thing. What we're going to do here, the vector calculus. The vector calculus operators measures vector fields quantitatively. Measures the vector fields quantitatively. Just a minute. Okay. Sorry for disturbance. See here. The vector calculus operators measures the vector fields quantitatively, comma, captures their nature, physical nature, and defines them mathematically unique. The vector calculus operators measures the vector fields quantitatively. Means what? Magnitude. Captures their physical nature and defines them mathematically unique. Clear? Yes. So the three things I need to justify. That one is magnitude, second one is a nature, third one is a uniqueness. So if you want to capture these three things, we have got a very powerful operator, what is called a differential operator. We have got a very powerful operator, a vector calculus operator, what is called a differential operator. Let me turn the page here. So we have got a differential operator. It is a very powerful operator. Differential operator. The differential operator is represented with a del is equal to dou by dou x cap plus dou by dou y cap plus dou by dou z cap. These are very powerful operators. It is just a mathematical operator by itself. It has got no meaning. Yes. So it is a differentiation of some function with respect to x oriented in the x. Differentiation of some function with respect to y oriented in the y. Differentiation of some function with respect to z oriented in the z. Yes. So what is this x cap, y cap, and z cap? These are called unit vectors. They are the vectors with the magnitude 1 oriented along the x comma, y comma, z direction. So here, differentiation of some function with respect, these are called unit vectors. So differentiation of some function with respect to x oriented in the x, differentiation of some function with respect to y oriented in the y, differentiation of some function with respect to z oriented in the z. This is called three-dimensional spatial derivative. Three-dimensional spatial derivative. Clear? So there are different ways of writing the unit vectors. You can write this one as x cap, y cap, z cap. The other one is ax cap, ay cap, az cap. The other way is I cap, j cap, k cap. The other one is ux cap, uy cap, uz cap. Throughout the subject, I'm going to use this one. Clear? Yes. Observe here. So let us try to operate this differential operator. Always remember, let me go back. Three things we need to investigate: magnitude, nature, and then uniqueness. Keep these points in your mind. I need to justify them. So I have got a very powerful operator, what is called a differential operator del. Now I'll operate this del on the vector field as well as on the scalar field. The other one is a scalar field. On the vector field, I can operate in a two ways. You would have learnt in your basics. There are two types of vector products are possible. One is you can perform what is called a divergence. One is you can perform what is called a curl. This is called divergence. And this is called curl if you perform the cross product. If you directly multiply with the scalar field, this is called a gradient. Or simply it is called grad. Okay, let us take one by one. Fine, let us start with the divergence here. I'll going to turn the page. The divergence of vector field. Listen carefully. Divergence is performed on the vector field. Output, let us see what happens. Now let us consider, let f is equal to fx x cap plus fy y cap plus fz z cap be a vector field. Okay. Now here f, the vector f is a vector is only because of this unit vectors x cap, y cap, and z cap. But what about this fx, fy, and fz? Fx, xy, and xz are scalar fields. Here it is fx, fy, and fz are scalar fields. Correspondingly, they are multiplied with the unit vectors so that the resultant is a vector. See, the actual way of writing fx is like this. Fx may be a function of x comma y comma z. Fy will be the function of x comma y comma z. Fz will be a function of x comma y comma z. Okay, fine. So it is a fx means what? It need not be only function of x. It could be, if you write this one explicitly, that is how you will look. Elaborately, that is how it looks. So let us try to perform the divergence. What is the divergence? It is a dot product between del and f. What is the del here? Dou by dou x x cap plus dou by dou y y cap plus dou by dou z z cap. Dot product with fx x cap plus fy y cap plus fz z cap. Okay. See here, how do you perform the dot product? Dot product is also called inner product. Yes, you can multiply these two, and these two. Okay, and the remaining all combinations are zero. Let me write down the dot product rules here. I'll going to justify that one in the coordinate system. Yes, what are the dot product rules? X dot x is equal to 1. Y dot Y is equal to 1. Z dot Z is equal to 1. Remaining all combinations are 0. X dot Y is equal to 0. Y dot Z is equal to 0. Z dot X is equal to 0. Y dot X is equal to 0. Z dot Y is equal to 0. X dot Z is equal to 0. Yes, so these are the dot product rules. Then you can ask why, how. That I'll justify later in the coordinate system. So after performing the dot product, what you will going to get? You will going to get divergence of F is equal to dou Fx by dou x plus dou Fy by dou y plus dou Fz by dou z. Yes, so this is a divergence formula. Divergence is performed on the vector field. Output is, there is no unit vectors here. There is no unit vectors here. So output is a, what is output? Output is, I want answers from your side. Divergence is performed on the vector field. Output is, what is output? Output is not just a scalar, it is a scalar field. You should add that word. Output is scalar field. Okay, fine. That means output is also different at the different locations that I'm going to show. Anyhow, now there is a terminology which you need to remember here. If a divergence of any vector is positive, then it is called source field. If a divergence of any vector is negative, then it is called sink field. If a divergence of the vector field goes 0, you need to remember this terminology. If a divergence of the vector field is 0, then it is called divergenceless, or it is also called solenoidal. Okay, well and good. These are the some of the terminologies which you need to remember. Fine, very good. But here, let us try to, you would have learned this formula in your mathematics also. But my interest is in physical interpretation. What it is? Physical interpretation. Let me turn the board here. Let me turn the page here. So if I perform the divergence on any vector field, what it will going to give? Net to flow on the small volume. Net flow absorbed on the small volume. What does that mean? Suppose let me talk about the net flow. What is the net flow, beta? Suppose if you consider some classroom, observe my example carefully. We're going to solve the questions after the Stokes theorem. Have some look over this. So if you consider some closed surface, something like a classroom, 50 students are entering from one door, 50 students are leaving from the other door. What is the net? Net is a 0. 50 entering, 50 leaving. Excuse. Suppose let us say 50 students are entering, 100 students are leaving. 50 entering, 100 leaving. Then there is a net flow. 100 entering, 50 leaving. Then also there is a net flow. So the net flow happens for the closed surface. Classroom is a closed surface. Suppose if you are having only one wall, one door, there will be only the flow, either inflow or outflow. For the net flow to happen, there must be a closed surface. There is a something like a balloon, something like a classroom. Yes. So what is the simple observation here? If you have a closed surface, in the closed surface, there will be a net flow. In and out. Suppose if you consider the open surface, something like a piece of a paper or one door, if you consider the open surface, there will be only the flow. In or out. Okay. Now let us take some examples here to understand this one. Observe here carefully. Example number 1. There is a vector field F1. Let us consider a water flow in the pipe like this. Okay, there is a pipe here. The liquid is flowing like this. Liquid flow is a vector here. Let us consider example number 2. There is a vector field F2. The liquid is flowing like this. More liquid is entering, less liquid is leaving. Example number 3. F3. Okay, it is something like this. Okay, fine. So there is a vector field here. Here, this is a vector field. This is a vector field. This is a vector field. I want to investigate the presence of divergence at that particular point. How can I investigate the presence of divergence? Speak out. According to this definition, you need to put some small box here. Inflow and outflow are same. So what happens at that location? The divergence is 0. Divergence of F1 is equal to 0. Suppose if you want to find out the divergence here, place some small box there. Here it is. Divergence of F1 is equal to 0. Suppose if I place some small piece of a box here, inflow and outflow are different. So the divergence of F1 is equal to 0. At the different points, there is a divergence. Now let us consider the second example. In the first example, in the second example, I have considered what kind of fields? Straightforward fields. In the third example, I have considered circulating fields. Listen carefully. Suppose if I want to investigate here, I need to place some small piece of a box. So divergence of F2 is equal to 0. If I place some small piece of a box, divergence of F2 is equal to 0. If I place some small piece of a box, how many lines are entering? 1, 2, 3, 4, 5 lines. How many lines are leaving? 2 lines. So what is the divergence of F2? Is not equal to 0. Now let us observe the third example. Let me place some small piece of a box here. Inflow and outflow are same. So what is the divergence here? Divergence of F3 is equal to 0. If I place some small piece of a box here, inflow and outflow are same, different. So there is a possibility for the divergence. Divergence of F3 is not equal to 0. What is the nature of the field here? It is straightforward. Here it is circulating. So what is this very interesting observation here? Circulating fields may also have divergence. Generally, there is a misconception regarding this curl and divergence for most of the students. They'll think that whenever I say divergence, they'll think something like this. Whenever I say curl, they'll think something like this. No, they are not nature of a vector field. Circulating fields may also have divergence. What is the meaning of divergence? If I place some small piece of a box, and if there happens to be a net flow from the small piece of a box at that location, there will be a divergence. Clear? Yes. So what is the extremely important statement you can expect here? Circulating fields may also have circulating fields may also have divergence. Circulating natured field or circulating fields may also have divergence. Extremely important statement. Clear? So we have individually defined the divergence. Let me focus on the curl as well. After that, I need to justify the 3 words. What are they? Let me go back. Don't forget these 3 words: magnitude, nature, and then uniqueness. Let me discuss the curl and divergence separately. So we have interpreted the divergence here. Now let us focus on the curl. Fine. So the curl of a vector field. Curl of a vector field. Okay. Let F is equal to Fx x cap plus Fy y cap plus Fz z cap BA be a vector field. Okay. So let us perform the cross product here. That is called a curl. Del cross F is equal to what it is? Dou by dou x x cap plus dou by dou y cap plus dou by dou z cap. Cross product with fx x cap plus fy y cap plus fz z cap. There are the rules for the cross product which you need to follow that I'll justify later. What are the rules for the cross product? There is a x cap, y cap, z cap. Here it is x axis, y axis, and then z axis. So you need to follow this circle by because we'll be using what is called a right-handed coordinate system. Clear? Yes. Observe here. So let me write down the cross product rules here. X cross y. X cross y is z cap. Y cross z is x cap. Z cross x is y cap. If I do reverse, I'll get minus. Y cross x is minus z cap. Z cross y is minus x cap. X cap z cap is minus y cap. X cross x is 0. Y cross y is 0. Z cross z is 0. So these are the cross product rules. See here, x cross x is 0. X cross y is z. X cross z is minus y. So this is giving the two terms. One is positive, one is negative. Similarly, this one, similarly, this one. Total after performing the cross product, you are going to get the 6 terms, out of which 3 are positive, 3 are negative. Fine. So for that one, writing in the determinant form would be one of the most appropriate and convenient form for us. It looks like a determinant form. Yes. Let me write down in the determinant form here. Del cross F is x cap. First you need to write the unit vectors x cap, y cap, and then z cap. Then the components of del. What are the components of del? Dou by dou x, dou by dou y, dou by dou z. Then the components of f. What are the components of f? Fx, Fy, Fz. Okay. So the output of the curl, if I perform the x cross y, in the output you will be getting the z cap, isn't it? So how do you perform the cross product here? X cap into this minus this into this. Y cap into this minus this into this. Z cap into this minus this into this. So in the output you will be having the unit vector. So what I mean to say here is, here the output of the curl is a vector. Output is vector field. You need to remember some terminology here. If the curl of a vector field goes 0, then it is called curl free. irrotational, conservative, what is that conservative? You will get later. What is the curl free? That means there is no curl. What is irrotational? I will going to explain. Okay. Now let us try to have the physical interpretation of this. Is a formula you should remember, and you should know the physical interpretation as well. Let us try to have the physical interpretation here. I'm going to turn the page. If I perform the curl on any vector field, it will going to give net rotation observed on small area. Net rotation observed on the small area. What does that mean? Let us take some example to appreciate this one. Let us consider example number 1. Water flow in the river. What is the water flow in the river? In general, it is a straightforward field, isn't it? In general, I am saying. In general, it is a straightforward field. Suddenly, if some leaf falls, if the water is moving forward, you would have seen the water is flowing. If the water is flowing in the river, suddenly some leaf falls, what happens? If suddenly some leaf falls, leaf will also move along with the water. Leaf will also move along with the water. Sometimes, even though water is moving forward, the leaf rotates. Even you can check this one. Just throw some bucket full of water and throw some pieces of paper. Okay. If I throw some pieces of paper, what happens? That object rotates. The paper rotates. Why this is happening? Even though water is moving forward, the object which is fallen onto the liquid rotates. Why this happens? This happens because difference in the velocities of water layer. According to the physics, water flow happens layer by layer. Yes, so the upper layer will move with a more faster velocity than its lower level, and so on. So because of the difference in the velocities of water layers, there will be some rotational effect created on the object which is placed in the field. Just forget about the physics. What is happening in the physics is none of our business. If you place some small piece of area, if that area is rotating, then you can say that there is a curl. If not, no curl. Okay. Let us take one other example here. Example number 2. Wash basin. Wash basin, generally what you use to wash your hands. There is a tap here. If I open the tap, what happens? There is a wash basin here, basin. Water will revolve and enter here. If I place some small piece of area here, small piece of area will also rotate along with the water. Will going to rotate along its own axis and also rotate along with the water. What is the nature of the field here? Here it is a straightforward field. Here it is a circulating field. Isn't it? So what is the simple observation here? What is the meaning of curl? Very extremely important. Straightforward fields may also have curl. What is the meaning of a curl? If I place some small piece of area, if that object is rotating, if that area is rotating, then you can say that there is a curl. At that location, there is a curl. Okay. So the straightforward, what is the important statement here? Straightforward. Natured fields may also have curl. Okay. Then one can ask, what is the fun of doing all these things? What is the divergence I have explained here? What is the meaning of divergence? Net flow from the small piece of a volume. What is the meaning of a curl? Net rotation observed on the small piece of area. Isn't it fine? So what we'll do, I'll going to club this divergence and curl together, and we're going to get very extremely important observations. Before that, it is a time to go for numericals on this curl and divergence. Number of times there are substitution kind of questions were noticed from these concepts. Yes. So the only thing is, in a 1 or 2 paper, you will find one question or two questions related to the 1 mark question or 2 marks question, which is related to the curl and divergence. Clear? Yes. So let us have the questions which are related to the curl and divergence. Yes. Okay, fine. The questions what I am going to solve in the classroom are collected from previous GATE, engineering services, ISRO paper, and I have added my own questions also, which are up to the level of GATE exam, and we'll also solve the volume number 1 questions in the classroom. Fine. So here is a question here. Check whether the vector field E is equal to yz x cap plus xz y cap plus xyz cap is solenoidal or conservative. Solenoidal means what? Divergence is zero. Conservative means what? Curl is zero. So you need to check for its curl and divergence, and from there you need to decide. Yes, as I'm doing first time, I'm going to explain the procedure. I'm going to explain the procedure of finding the curl and divergence. So every year there is a question on this curl and divergence. It is a very simple, you can easily score marks. Okay, only thing is you should not do any algebraic errors while dealing with this one. Clear? And you should know the terminology. Solenoidal, conservative, irrotational, curl free. Clear? Fine. Find out its divergence. What is the divergence of E? It is dou by dou x of x component is yz plus dou by dou y of y component is xz plus dou by dou z of z component is xy. It is a partial differentiation. What is the meaning of partial differentiation? If you know the answer, you can try. If you know the procedure, you can try, and you can later you can cross check. Yes. So what is the meaning of partial differentiation? When you are differentiating with respect to one variable, other variables are treated as a constants, isn't it? So here you are differentiating with respect to x, y and z are constant, x and z are constant, x and y are constants. So what is the divergence of E? Zero plus 0. So here it is. Divergence of E is equal to 0. So E is a solenoidal. Then what about the curl here? Curl of E. X cap, Y cap, Z cap, dou by dou X, dou by dou Y, dou by dou Z. Then X component. What is X component? Here it is YZ. Y component is XZ. Z component is XY. Clear? How do you perform the cross product here? Curl. How do you find out the determinant of the 3 by 3 matrix? Yes, observe here. If you talk in terms of mathematics, you will call it as a minor, cofactor, and all that story. But I do not talk in that terminology. Here, throughout our subject, we'll be dealing only with the 3 by 3 matrix. So remember it as a formula. What is the formula? X cap into this minus this into this. Isn't it? Yes. So here it is. X cap into dou by dou y of xy minus dou by dou z of xz. Next one is a minus y cap into, isn't it? Minus y cap into this minus this into this. Minus y cap into dou by dou x of xy minus dou by dou z of yz. Last one is a z cap into this minus this into this. dou by dou x of hz minus dou by dou y of yz. Del cross E is equal to x cap into, here it is, what is after differentiation? X minus x minus y cap into y minus y plus z cap into z minus z. So what is this curl of E? 0 x cap minus 0 y cap plus 0 z cap, or simply you can write it as a 0. So what is this E? E is a conservative as well. It is solenoidal as well as conservative. Okay, let us have one more question. I'm going to turn the page. This was ESC question. The nature of the vector field A is equal to A is equal to 3x square yz x cap plus x cube z y cap plus x cube y minus 2z z cap is, options are given: rotational, option B divergenceless, option C solenoidal, option D conservative. Yes. See here, you can observe from here what is the meaning of divergenceless and solenoidal. It is same. Divergence is equal to 0. What is the meaning of conservative? Curl is equal to 0. What is rotational? Curl is not equal to 0. Yes or not? So answer cannot be B and C. Check only for its curl. If the curl is 0, option D is answer. If curl is not equal to 0, option A is answer. Clear? So find out its curl. X cap dou by dou x 3x square yz. Here it is y cap dou by dou y x cube z. Here it is z cap dou by dou z x cube y minus 2z. Curl of A, x cap into this minus this into this. I'll write down directly. Can I write down directly? What is this into this? Here it is x cube minus x cube minus y cap into this minus this into this, which is 3x square y minus 3x square y plus z cap into this minus this into this, which is 3x square z minus 3x square z. So here it is curl of E is equal to 0. Means what it is? Conservative. Option D is answer. Let us have one more question, beta. This was asked in the gate paper for 2 marks. I am going to turn the page. But in the EC paper, it doesn't matter. Given irrotational vector field F is equal to K1 into XY plus K2 into Z cube X cap plus three x square minus K2 into Z Y cap plus 3x Z square minus Y Z cap. Then the vector, then the divergence of F at 1, 1, minus 2 is, options are given 6, option B minus 6, option C 12, option D minus 12. Actually, this was a numerical answer type question. Yes, what should I do? What is answer? Speak out. Find out its divergence. Yes, find out its divergence at 1, 1, minus 2. Divergence of F is equal to dou by dou x of K1x plus K2 into Z cube plus dou by dou y of 3x square minus K2 into Z plus dou by dou Z of 3x Z square minus y. What is the divergence of F? Here it is K1 into y plus 0 plus 6xz. So here it is divergence of F is equal to K1 into y plus 6xz. At what point is asking? at 1 comma 1 comma minus 2. Just substitute there. Divergence of f k1, it is 1 plus 6 into 1 into minus 2. Divergence of f is equal to k1 into minus 12. But what is it is? It is a numerical answer type question actually. Anyhow, I have provided options here. You want to find out the k value. It is an incomplete question. Any information, extra information to find out the k1 value? Yes. Any extra information given in the question to find out the k1 value? Come on, speak out. In the question it is mentioned that it is a irrotational vector. Yes, read the question properly. It is mentioned that it is a irrotational. So what is the meaning of irrotational? Its curl is equal to 0. Let me turn the page here. Curl of f. What it is? X cap dou by dou x component. What is x component? This is a x component. So what it is? K1 into xy plus K2 into z cube. Here it is y cap. Dou by dou y, there is a y component. What is the y component? This is a y component. Let me write down the y component. Here it is 3x square minus K2 into z. Z cap. Dou by dou z. What is the z component? Let me go back. Here is a z component. Here it is 3x z square minus y. It is said that it is equal to 0. Means what? It is a null vector. This can be written as 0 x cap plus 0 y cap plus 0 z cap. Yes. So what is required for us? K1 value is required. So just to search for K1 value, I'll equate the x components on both sides here. What is the x component here? This into this minus this into this. If I do this into this and this into this, there is no K1 value. Now let us focus on the y component. This into this minus this into this. What is this into this? There is no K1. What is this into this? After differentiation, there won't be any K1. Clear? Without wasting our time. Z component. This into this, there is no K1. But this into this, yes, there is a K1. So what I'll do, without wasting our time, I'll going to equate the Z components on both sides. What is the Z component on the left side? Dou by dou x of 3x square minus K2 into Z minus dou by dou y of K1 xy plus K2 into Z cube is equal to 0. So here it is 6x minus K1 into x is equal to 0. 6 minus K1 into x is equal to 0. From here, six minus K1 is equal to 0. K1 is equal to 6. Let me go back. K1 is equal to 6. So what happens? Resubstitute here. divergence of f is equal to 6 minus 12, which is equal to minus 6. Clear? Let us take one more question. I'm going to turn the page here. This was asked for 1 mark in the gate paper. Simple and straightforward question. Given a vector field, A is equal to x plus az x cap plus y plus bx y cap plus x plus cz z cap. Then the value of C such that the vector is solenoidal. Option A -1, option B -2, option C -3, option D 0. What is the answer for this? Yes, yes. It is a solenoidal. Solenoidal means what? Divergence is 0. Yes or not? Here is a vector field. You need to find out the C for solenoidal. Divergence of A is equal to 0. Here it is dou by dou x of x plus az plus dou by dou y of y plus bx plus dou by dou z of x plus cz is equal to 0. So here it is 1 plus 1 plus c is equal to 0. C is equal to -2 is the answer. It's a very simple and straightforward. So these kind of questions are regularly noticed in your papers. Clear? Yes. Fine. So what we have done so far? So you should not forget these 3 words. What they are: magnitude, nature, and then uniqueness. What does that mean? We have explained, I've explained here divergence and curl separately, isn't it? I said that the divergence, what is the interpretation of the divergence I have given? Net flow from the small piece of a box. What is the meaning of a curl I have given? Net rotation observed on the small piece of area, isn't it? Then what is the fun of all these things? Net flow, net rotation. Then in what way it will going to help us? Okay. So to have the further insight into the Maxwell's equation, further insight into the divergence and curl, let us have some examples here. What we're going to do, we'll take some 4 examples. Yes. So we're going to take 4 examples that will give the further insight into the divergence as well as the curl. Examples of examples of vector fields. Examples of examples of vector field responsible responsible for both responsible for curl and divergence or divergence and curl. Divergence comma curl. Clear? Yes. Now I'm going to take those 4 examples parallelly so that you can compare them and you can make some very interesting observations. Clear? But this would be the appropriate time for us to go for a break. Okay? Every 2 hours, we're going to have a break so that you can refresh and you can come back. Clear? Yes. So we're going to take 20 minutes break. After that, we're going to have the further insight into the divergence and curl, which is very interesting results we're going to get. And after that, in the today's session itself, we're going to take a gradient operator. Okay. And at the end of we're going to dedicate, we'll finish today's session little bit early so that I can interact with you, so that I can know to what level you are and how you are following. Okay. We're going to have some interaction session. We're going to have doubt clearing session at the end of the discussion. Clear? We'll continue after the break. Okay, welcome back, friends. Excuse. Okay, let us focus on examples of vector fields responsible for curl, comma, divergence. Now let us take some 4 examples here. Observe here, I'll take some 4 straightforward fields. This is the first field F1. Second one, observe carefully. Second one is something like this. It is second type of field, F2. F3 is something like this. I've considered some 4 examples to have the further insight into the divergence and curl. What is the nature of the field? It is oriented like this, and its magnitude is increasing, increasing, further increasing. So it is increasing, increasing, further increasing. So what you can say, its magnitude is changing. Its magnitude is changing, or here it is increasing. Along the listen carefully. The magnitude of the vector field is changing along the direction of orientation. What it is? What you can comment on the nature of the field? The magnitude of vector field is changing along the direction of orientation. It is oriented like this, increasing, increasing, further increasing. Listen carefully. What is the nature of the second charge, second field? It is oriented like this, but its magnitude is increasing, changing like this. So the vector field is oriented like this, but its magnitude is changing like this in the perpendicular direction. So what you can comment here, the magnitude of the vector field is changing perpendicular to the direction of orientation. It is oriented like this, but its magnitude is changing like this. So what you can comment here, the magnitude of vector field is changing along the perpendicular to the direction of orientation. Yes, so listen carefully. It is like this, it is changing like this, oriented like that, but here it is oriented like this, but it is changing like this. Now let us try. What you can comment on the third one and fourth one? Its magnitude is changing along the direction as well as in the perpendicular direction, isn't it? So here it is 2, here it is 2, here it is 5, here it is 2, 2. It is changing like this, it is changing also like this. Here it is 6, something 5, here it is 6. It is changing like this as well as like this. So here the magnitude is changing along the direction as well as in the perpendicular direction. Magnitude is changing along and perpendicular direction. What about the fourth one? Same story. Magnitude is changing along and perpendicular direction. Yes, observe the carefully. The first one is like this, increasing, increasing, further increasing. Second one is it is oriented like this, but its magnitude is changing. Third one it is changing like this and like this. Fourth one also like this and like this. First one and second one are special fields. In the first one, the magnitude is changing along the direction of orientation. Second one, the magnitude is changing perpendicular to the direction of orientation. Yes, observe carefully here. Let me give some naming here. Here it is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. How do you find out the and here? 4, 3, 2, 1. 4, 3, 2, 1. 4, 3, 2, 1. How do you find out the divergence? Let us try to investigate the divergence and curl. How do you find the divergence here? Listen carefully. You need to place some small piece of a box here. How much is entering? 2. How much is leaving? 3. So there will be a divergence here. Divergence of F1 is not equal to 0. Then how do you investigate the presence of curl? By placing a small piece of area. Listen carefully. I need to place some small piece of area here. If I place some small piece of area, 3 is acting above, 3 is acting below, so it will not rotate. Yes, fine. So what about the curl of this one? Curl of F1 is equal to 0. Now let us observe the second one here, second example. So if I place, how do you investigate the divergence? Place some small piece of box. How much is entering? 7. How much is leaving? 7. So what about the divergence here? Divergence of F2 is equal to 0. Then let us try to investigate the curl. I'm going to place some small piece of area here. 4 is acting above, 3 is acting below, it will rotate. Yes. So how does it will rotate? It will rotate like this. So here, curl of F2 is not equal to 0. So what you can say here? What you can say is a simple observation. The vector field whose magnitude is changing, first case, the magnitude is changing along the direction of orientation will have divergence. In the second case, the vector field whose magnitude is changing perpendicular to the direction of orientation will have curl. That means what is this divergence is talking about? The divergence is explaining how the vector field is changing along the direction of orientation. What is this curl is saying? This curl is saying how the vector field is changing in the perpendicular direction. What is the behavior of the vector change in the perpendicular direction? So if the vector field is changing along the direction of orientation, it will have divergence. If the vector field is changing perpendicular to the direction of orientation, then it will have curl. The vector field, I need answers from your side. The vector field whose magnitude is changing along and perpendicular will have, along and perpendicular will have, along and perpendicular will have, speak out, will have, both curl and divergence. Both curl and divergence. The vector field whose magnitude is changing along and perpendicular will have both divergence and curl. In general, arbitrary field F3 and F4 are arbitrary fields. It is arbitrary field. Here it is arbitrary field. F3 and F4 are arbitrary fields. Okay. F3 and F4 are arbitrary field. Arbitrary fields can have both divergence and curl. F1 and F2 are some special fields I have considered. Only variation along the direction. Curl, perpendicular. That means if you want to know the complete description of a vector field, that means if you want to understand how the field is changing in the three-dimensional space, how it is changing along the direction, how it is changing in the perpendicular direction, if you want to understand, you must define the curl and divergence. You must define its both curl as well as divergence. Okay, see here. So if this here the F3 and F4 are having a both curl and divergence, but as far as F3 and F4 are different, their set of curl and divergence will be different. F3 and F4 may have the same curl, but they'll differ with the divergence. If they are having a same divergence, they'll differ with the curl. vector fields will have a same set of curl and divergence, which is given by what is called a vector Helmholtz theorem. The exact definition of the vector Helmholtz theorem is not important for us. What is important is the gist of the theorem. The gist of the theorem is any arbitrary vector field can be uniquely defined by specifying both its curl and divergence. If you know the curl and divergence of vector field, that implies everything about the vector field. Okay, how the vector field is changing along the direction and perpendicular direction, how the vector field is changing in the three-dimensional space, that information is existing inside the curl and divergence. Let me turn the page here. So let me write down the statements here. Any arbitrary vector field can be uniquely defined. Any arbitrary vector field can be uniquely defined by specifying both its curl and divergence. This is a powerful statement. Now let me write down the next statement here. I want to little bit elaborate this one. So the complete description of the vector field in the three-dimensional space is possible by defining. So how, if you want to understand how the vector field is changing, that information is existing inside the curl and divergence. Observe here, the complete description of vector field in the three-dimensional space is possible by defining both its curl and divergence. Now let us consider once consider those Maxwell's equations. Why these Maxwell's equations are such a popular equations? Consider first Maxwell equation. What it is? Del cross H is equal to J plus dou D by dou T. Second Maxwell equation. Del cross E is equal to minus dou B by dou T. Third Maxwell equation. Divergence of D is equal to divergence of epsilon into E is equal to rho V. Fourth Maxwell equation. Divergence of B is equal to divergence of mu into H is equal to 0. What is the first equation here? It is the curl of H. Second equation, curl of E. Third equation, divergence of E. Fourth equation, divergence of H. So why these Maxwell's equations are such a popular? Why? Because they are defining the curl and divergence for both electric and magnetic field vectors. That means they have got a complete information of both electric and magnetic fields, isn't it? So what Maxwell's equations are doing, basically, they are defining the curl and divergence for both electric and magnetic field vectors. Okay, and what these are? These are the sources. What are the sources? There are two types of sources. One is a charge, other one is a currents. Okay. So what is the note here? Why Maxwell's equations are very popular? Why mathematically seeing? What is the mathematical perspective of them? They are defining the curl and divergence for both electric and magnetic field vectors. It means they are having a complete information of both electric and magnetic field vectors. Okay, fine. So let me write down here. Maxwell's equations are what it is? Why they are such a popular equations? Maxwell's equations are defining curl and divergence for both electric and magnetic fields. Maxwell's equations are defining curl and divergence for both electric and magnetic fields and establishes relation with their respective what are the sources in brackets in the electrical engineering how the sources can be classified. One is a charge, other one is a currents, isn't it? So they are charges comma currents. So the complete information of the complete information of the complete information of electric and magnetic fields exist inside the curl and divergence, isn't it? So how the vector field is changing in the three-dimensional space can be obtained by defining both its curl as well as divergence. Excuse. This is all about the curl and divergence. Okay. Let us focus on the next operator, what is called a gradient operator, isn't it? Operator we have seen on the vector field. Now let us see on the scalar field here. Now let us see one more operator, the gradient operator. The gradient of scalar field. The gradient of scalar field. Okay, let us f of x comma y comma z be a scalar field. Up till now we have seen the characterization of the vector field. Now let us see the scalar field. Just for that thing, to make the thing simple, I'll call it as f of x comma y comma z. I'll call it as a f. So what is the gradient here? Del into f. What is the del? Dou by dou x cap plus dou by dou y cap plus dou by dou z cap into f. So what it is? Gradient of f is equal to dou fx by dou x cap plus dou f by dou y cap plus dou f by dou z cap. So the grade on the scalar field, output is a vector field. We are having a unit vectors here. So what is output here? Output is a vector field. So whenever I say the vector field, it will have a magnitude as well as direction. Yes. What is the magnitude here? What is the magnitude? Magnitude is equal to square root of dou by dou x square plus dou f by dou y square plus dou f by dou z square. And other one is a direction. What is the direction? Direction is represented with the cap, which is r by its magnitude. Okay, let us try to have the physical interpretation of this one. What is this gradient is indicating? It is performed on the scalar, but output is a vector. What does that mean? It is performed on the scalar, but output is a vector. What does that mean? Suppose let us take the temperature. What is the temperature? Temperature by nature it is a scalar quantity, isn't it? Temperature by nature it is a scalar quantity. But you are standing in the hall, and if you start moving towards the kitchen, what happens? You will find raise in temperature. If you start moving towards the kitchen, you will find raise in temperature. If you start moving towards the AC, what happens? You will find fall in temperature. Temperature is just a number, 22 degrees, 28 degrees. 36 degrees. Temperature is it is a number. Are going in a different directions. Suppose if you are standing in the hall and if you start moving towards the kitchen, what happens in temperature? But if you start moving towards the AC, you will find fall in temperature. This direction temperature is increasing. This direction temperature is decreasing. So the quantity by nature, which is a scalar quantity, but its variation is a vector. Such a physical phenomena, excuse, such a physical phenomena is mathematically captured by the gradient operator. Let me reiterate what I am saying. Quantity by nature, which is a scalar quantity, but its variation is a vector. Such a physical phenomena is mathematically captured by the gradient operator. Let us have some examples here. Let us have some example. I'll elaborate this one and we're going to see the interpretation of the magnitude and direction. Let me turn the page here. I'm going to take what is called isotherms. What is the meaning of isotherms? Equi-temperature surfaces are called isotherms. You would have seen something like this in your newspaper. Something like this. What these are? Equi-temperature surfaces. Something like this. Something like 28 degrees, 26 degrees, 24 degrees, and so on. What these are? Equi-temperature surfaces. That means somewhere around here in the Kerala, somewhere around here in the Tamil Nadu, temperature is some 28 degrees. Somewhere around here in the Maharashtra, Telangana, Andhra Pradesh, something like that, the temperature is 26 degrees. Somewhere around here in the Gujarat or Maharashtra, Madhya Pradesh, something like that, the temperature is 24 degrees. Yes, here my question here is, I am standing on this surface and I am running towards this surface in a different directions. In which direction I am going to get a sudden change in the temperature? What I will do, I will draw only this portion. Just forget about all the story. Let us consider the two surfaces. What these two surfaces are? Equi-temperature surfaces. What these two surfaces are? Equi-temperature surfaces. Equi-temperature surfaces are isotherms. Equi-temperature surfaces. Let us say the temperature on this one is T naught. I want to generalize this problem. T naught at a location of x naught comma y naught comma z naught. Here it is T1 at the location of x1 comma y1 comma z1. The temperature difference between these two surfaces is delta T and the distance is delta L. I want to go from this surface to this surface. I want to go from this level surface to this level surface, T0 to T1. In how many possible ways I can go? Infinite number of ways. I can go like this. Here it is delta L0. I can go like this, delta L1. I can go like this, delta L2. Isn't it? What is the speciality of this one? This is a normal. Normal to the level surfaces. So here my question is very simple. In which direction you will find sudden change in temperature? Is it in the delta L0, 1 or 2? I'm standing on one level surface going to the other level surface. So in which direction you will find sudden change in temperature? Come on, speak out. In which direction? Delta L0. Smallest distance. Smallest distance. Very good. L0. Normal. Okay. Different answers. Smallest distance you will find sudden change. Let me give you some simple analogy. Let me turn the page here. Suppose you are standing in the roof. You are standing on the roof. Floor, and there is a roof here in your living room. There is a floor here, there is a roof here. I want to go from floor to the roof. How I can go? Directly I can tie the rope and I can go directly like this. Isn't it? I want to go from this surface to this surface. Some 20 feet surface to 30 feet surface or 70 feet surface, whatever it may be. Or 70 feet surface, whatever it may be. If I draw a line and if I put a dots, what does that indicate? It indicates a surface like this. I want to go from this surface to from flooring to the roof. Flooring, here is a flooring and here is a roof. How can you go direct? You can just tie a rope there and you can go like this. Isn't it? Suddenly you can go like this. If you are weak, you can go by steps like this. Or if you are still weak, you can go with us very small steps. Or you can go like this also. So in which direction you will find sudden change in the height? Normal direction. Generally this is called steep. So in which direction you will notice the steep sudden change in the height? Normal direction. So here also you will find sudden change in the temperature in which direction? Normal direction. So this is called a gradient. So here it is delta T by delta L0 is greater than delta T by delta L1 is greater than delta T by delta L2. Yes, So this is maximum. Yes or not? This is maximum. So this is called gradient. Yes. So what is the definition of gradient here? Gradient is dt by dl n cap. Or you can also say this is a maximum. Let me go back here. So what is this magnitude is indicating? Maximum rate of change of scalar quantity in the three-dimensional space. What it is? Maximum rate of change of scalar quantity in 3D space. So that maximum occurs in which direction? Normal direction. Normal to what? Level surfaces. In our example, I have taken it as a equi-temperature surfaces. It could be equi-pressure surfaces, or it could be equi-potential surfaces. In our subject, we're going to have what is called equi-potential surfaces. Later in the electrostatics, we'll get. Yes. Someone is saying by lift here. Isn't it? If you go by the lift, you'll find sudden change in height. So what it is? Here, which is equal to normal. Normal to what? Normal to the level surfaces. Normal to the level surface. Clear? Fine. Let us have one question here. The scalar field in certain region is defined as 3x square yz. Question A. Find its gradient. Question B. The direction of unit normal. The direction of unit normal acting on level surface at the point 1, 1 is The direction of unit normal acting on level surface at the point 1 comma 1 comma minus 1 is excuse 1 comma 1 comma minus 1 is. The first part of the question is very straightforward. Is asking us to find out what is called a gradient. Yes. Now let us consider here is a scalar field. I'll represent it as a F. 3x square yz. Question A, you need to find out the gradient. What is the gradient formula? Dou fx by dou x cap plus dou f by dou y cap plus dou f by dou z cap. So what is the gradient of f? 6x yz x cap plus 3x square z y cap plus 3x square y z cap. It is very straightforward. What is the second part of the question? He is asking the direction of unit normal. What should I do for the unit normal? Speak out. What should I do for the unit normal? How I can get the unit normal? Gradient direction itself is a normal direction. That is what I was saying. Isn't it? Yes. Divide by the magnitude at some particular. That is what I was saying. Interpretation. What is the interpretation here? The gradient direction itself is a normal direction. I'm going to turn the page here. What is the gradient direction? Normal direction. Vector by its magnitude. What is the vector? At what point? 1 comma 1 comma minus 1. So here it is 6 into 1 into y into x cap plus 3 into 1 square into minus 1 into y cap plus 3 into 1 square into 1 into z cap divided by square root of 6 square plus minus 3 square plus 3 square. So how much is this? Six x cap minus 3y cap plus 3z cap. How much is that? 36 plus 18. So which is 54. So what is the gradient direction? Is nothing but a normal direction, which is 6x cap minus 3y cap plus 3z cap divided by square root of 54. Okay, so what is the interpretation of the gradient? This is the interpretation of the gradient. What is the magnitude of the gradient is giving? Maximum rate of change of scalar quantity in the three-dimensional space. And what is the direction normal to the level surfaces? Clear? Yes. Yeah, just a minute here. Small correction. Here it is minus 1, minus 6. So here it is minus 1. Here it is minus. Here it is minus. There is a one more operator. Let me turn the page here, which is a derived operator. Let us discuss that one as well. Laplacian operator. What it is? Laplacian operator. What is a Laplacian operator? Here it is, derived operator. Del dot del, which is dou by dou x x cap plus dou by dou y cap plus dou by dou z cap. Dot product with dou by dou x cap plus dou by dou y cap plus dou by dou z cap. Yes. So this will be written as dou square, which is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. If you apply the laws of dot product, this is of dot product. This is the formula need to be remembered. That is the thing. Yes, so it is a derived operator. It has got no physical significance. The only thing what I can say here is later in the electrostatics, we're going to use this one in understanding what is called Poisson's equation. So what we can write here is useful in Poisson's equation. Note, you need to remember one terminology here. If a Laplacian of any function goes 0, then it is called harmonic function. Okay, this is a terminology one should remember. And one more thing here, there are some null identities which are taken from the vector calculus. Later we're going to use these things, null identities. There are two null identities. First one is divergence of curl of a vector is always 0. I am putting the 3 lines. It is equivalent. You can take any vector, this is true. Divergence of a curl of a vector is always 0. Number 2, curl of a gradient of a scalar is always 0. It is not true for particular scalar. You can just substitute whatever the scalar you like. You can show LHS is equal to RHS. So we'll going to take especially this one later. We're going to use this one later. Anyhow, you learn these things in your vector calculus because we'll be in the use of this one later. That is the reason why I've considered that. Yes, let us have one question before closing the session. Find value of k for harmonic function. Sin hyperbolic x cos ky into e to the power of pz. Find the value of k for harmonic function sin hyperbolic x cos ky into e to the power of pz. Let us consider that as a scalar field f. Sin hyperbolic x cos ky into e to the power of pz. So what is the harmonic function? Del square f is equal to 0. So which is dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square is equal to 0. Just substitute this one there. Dou square by dou x square of sin hyperbolic x cos ky into e to the power of pz plus dou square by dou y square of sin hyperbolic x cos ky into e to the power of pz plus dou square by dou z square of sin hyperbolic x cos ky into e to the power of pz is equal to 0. So what is the double differentiation? Here you need to double differentiate this one. Here you need to double differentiate this one. Here you need to double differentiate this one. Let me turn the page here. What is the sin hyperbolic h double differentiation? What is the one-time differentiation? Cos hyperbolic x. One more time differentiation, it is sin. Here it is a hyperbola. What is the cos ky? One-time differentiation is minus k sin ky. One more time differentiation is minus k square into cos ky. What is this e to the power of pz? One time differentiation is p into e to the power of pz. One more time differentiation p square into e to the power of pz. So what happens? Just substitute there. Here it is. Sin hyperbolic x cos ky into e to the power of pz plus what it is? Sin hyperbolic x minus k square into cos ky into e to the power of pz plus sin hyperbolic x cos ky into p square into e to the power of pz is equal to 0. Now you can bring this one common here. Sin hyperbolic x cos ky into e to the power of pz. Sin hyperbolic x cos ky into e to the power of pz is equal to 0. Now you can bring this one common here. Sin hyperbolic x cos ky into e to the power of pz. Sin hyperbolic x cos ky into e to the power of pz is equal to 0. Now you can bring this one common here. Sin hyperbolic x cos ky into e to the power of pz is equal to 0. Here it is 1 minus k square plus p square is equal to 0. So this is given in the question. It is a given function. So obviously this must be equal to 0. That means 1 minus k square plus p square is equal to 0. Here k is equal to plus or minus square root of 1 plus p square. Yes. So what we will discuss in the today's session, let us have some fast recapitulation. So these are syllabus: vector calculus and coordinate system, electrostatics, magnetostatics, time varying fields. So that is a weightage given for this subject. Initially we had some motivation that if you want to understand the different electrical engineering aspects, the common thread which is running behind all these things is a EM phenomena. To put it in a simple words, what is the EM phenomena? Time varying electric field giving magnetic field and magnetic field giving electric field is called EM phenomena. Okay, and that is explained by what is called Maxwell's equations. That is explained by what is called Maxwell's equations. And Maxwell's equations are explaining what is called EM phenomena. And if you want to understand the Maxwell's equations, you must be reasonably good at what is called vector calculus. And that is the reason why your topic number 1 is dedicated for the vector calculus. So with that motivation, we have started our discussion on the vector calculus. I would define what is called I have defined what is called I have defined the field. I have explained with some examples, and I have taken some examples to give the visualization of the field. Especially the water flow in the river, other one is the air distribution around the fan. So the magnitude, nature, and uniqueness, these are the attributes of the fields which can be achieved by the differential operator, can be operated on the vector field as well as in the scalar field. On the vector fields, two types. One is you can perform the dot product, other one is you can perform the cross product. So this is the divergence. This is a formula need to be remembered, which I have kept here. Okay. Along with that, here is a interpretation. Net flow from the small piece of a box. Here it is a curl. There is an interpretation. Net rotation observed on the small piece of area. You have seen some questions. And to have the further insight into the curl and divergence, we have taken some examples that the vector field whose magnitude is changing along the direction of orientation will have divergence. The vector field whose magnitude is changing perpendicular to the direction of orientation will have curl. The vector field whose magnitude is changing along and perpendicular will have both curl and divergence. If you have some two arbitrary fields, they'll never will have they will never have the same set of curl and divergence. If they are having a same divergence, they will differ with the curl and vice versa. So what is the mathematical definition of uniqueness? Any arbitrary vector field can be uniquely defined by specifying its both curl and divergence. Clear? So interestingly, the Maxwell's equations are defining curl and divergence for both electric and magnetic field vectors. So next one is a gradient. What is the gradient is? It is operated on the scalar field. Output is a vector, and the magnitude is indicating maximum rate of change of scalar quantity in the three-dimensional space, and the direction is normal to the level surfaces. That maximum rate happens in the normal direction. So there are, I have taken it as isotherms to explain this concept, but there could be equi-temperature surfaces, equi-pressure surfaces, equi-height surfaces, equi-potential surfaces. In our subject, we are going to have equi-potential surfaces. And we have seen one Laplacian operator, which is a derived operator. This will going to help us in understanding what is called a Poisson's equation. And there is one terminology and null identities which we need to remember, which are taken from the vector calculus. Okay, just raise your hand, I will come to you. If you want to talk anything, ask anything.
Hello, good evening, sir.
Yes.
Good evening.
Yes,
sir,
yes.
I have talked in a gradient that you said that that is the maximum rate of change.
Oh.
Maximum rate. But how it will be maximum rate? Because in the if we are taking some vector that is x, y, z point, every instant it will be the direction is changing. The maximum rate of change is the perpendicular direction. Each is the not perpendicular direction. Each for x different values of x, that may not be the perpendicular direction.
That is what I am changing. I am showing here. Perpendicular direction is a maximum change.
But sir, that change is defined by dou f by dou x. Let's suppose we are taking some example. That is dou f by dou x. That is dou f by dou x will be maximum. Is that at that point?
Yes.
That is dou f by dou x is a function only.
Yes, it is a function.
Function. That function have multiple minima and multiple maxima. Then how we know that by substituting that point, that will be the maximum or that will be the minimum. This is the maximum rate of change.
You need to substitute. If you substitute all the points, that will go to show the normal direction.
But for a function, there may be number of maxima minima, but one will be a most that will be the some are local maxima, some are globally maximum.
Absolute maximum. Yes, you are correct.
But at that point, in the given question, it is just given a point, and we are calculating the maximum rate, the rate of change. Then how we know that this is the maximum only? Because for that function, anything be maximum.
If you consider this point, compared to other direction, this is maximum. If you consider this point, compared to these things, it is maximum.
Will it happen actually, sir?
If you consider this point, this is
not understandable.
This one.
Okay. Means for that point, this will be maximum.
Maximum. At what point considering compared to other things, that is maximum. From that surface, that will be maximum. You can have other level surface as well in between.
Okay. Thank you.
Mohammed.
Hello, sir. Hello, sir.
Sit.
Am I audible, sir?
Yes.
Sir, that uniqueness character attributes of field you have explained, sir. Sir, can you please tell that one more time briefly?
See, according to observation, no two vector field will have the same set of divergence and curl.
Okay.
If you have a vector, if you consider two vector fields, this vector field is having curl and divergence. This is also having curl and divergence. Let us say if these two vectors are having a same divergence,
Yes.
curl, they will have different divergence. So the set of divergence and curl is unique for a given vector.
Okay. Sir, it can be of same type, or I mean, if we are considering two different electric fields only, sir.
We'll come to electric field later. Just to be because
yes, sir. It means there will be only 4 vector fields only, na, sir. Yeah. Got it, sir. Got it. Thank you, sir.
Okay. Shiva G.
Sir, good evening, sir.
Okay.
Sir, at 18F, sir. Sir, could you explain how the curl of that F2 is not equal to 0?
Here 4 is acting. Consider it force. Here 3 is acting.
Okay, sir.
If you treat something like a force, you are applying a more force here, let force here. So object will rotate or not, isn't it? You are applying the more force here compared to this one. Object will rotate.
Sir.
The equal force, it will move forward. If you apply more force here, it will rotate.
Oh, okay, sir. So then what about the first one, sir? Like F1? Why it is 0?
3 and 3.
Oh, okay. Got it.
It will move forward, but no rotation.
Yes, sir. Sir, and then one more thing is that arbitrary, like vectors, arbitrary functions, sir. So they have the magnitude and direction changing in both perpendicular and in along the direction of orientation. So that's why they're like arbitrary constants.
Yes.
Sorry, arbitrary. Okay, sir. Yes, sir. That's it, sir. Thank you.
Okay. Good night.
Hello, sir. Can you repeat the second null identity?
Curl of a gradient of a scalar is 0. Written on the screen. Curl of a gradient of a scalar is 0. Always 0. It is equivalent.
Okay, sir.
Okay. Pandey.
Hello.
Yes, but
Sir, F14F.
14F.
Sir, how you have neglected the options B and C?
Divergence means what? Divergence less means divergence is equal to 0, isn't it?
Yes, sir.
Solenoidal also means divergence 0. Answer cannot be B and C. It is a multiple choice question. Any one of can be the answer. Isn't it?
Yes, sir.
I'm comfortable. Yes. Any more questions?
Sir?
Mohammed.
Sir, you have explained about the example of curl, sir, curl of a vector quantity, that wash basin example. Sir, practically what its significance I'm not able to understand, sir. That rotation and all.
That is what I have kept the divergence and curl here and I have explained. Says only to current, what ultimately what I'm saying here is current describing the vector in the three-dimensional space. If you want to understand vector field, what is the language you are comfortable? Hindi, Telugu.
हिंदी
देखिए इधर,
यस
जो आप वेक्टर फील्ड को थ्री डायमेंशनल स्पेस में उसका वेरिएशन बिहेवियर कैसा है
हाँ सर
जानकारी होने के लिए आप उसका कर्ल और डाइवर्जेंस डिफाइन करना चाहिए.
ओके सर उसको उसकी ये दो प्रॉपर्टीज है ना सर तो उससे अपन क्या क्या मालूम होता अपने को वो है ये है बोल के ऐसा
और लिखा मैंने, देखिए एनी ऑर्बिट सेकंड स्टेटमेंट पढ़िए, द कंप्लीट डिस्क्रिप्शन ऑफ ए वेक्टर इन द थ्री डायमेंशनल स्पेस, मतलब उसका वेरिएशन कैसा है थ्री डायमेंशनल स्पेस में, वो कैसा वो वेरी हो रहा है अलोंग द डायरेक्शन में और परपेंडिकुलर डायरेक्शन में, उसका वेरिएशन कैसा है, उसका बिहेवियर कैसा है, जानने के लिए आप वो वेक्टर का कर्ल और डाइवर्जेंस डिफाइन करना चाहिए. कर्ल और डाइवर्जेंस का अंदर वो इंफॉर्मेशन रहेगा.
ओके सर और एक है सर अब अपन एक दो प्रॉब्लम सॉल्व करें ना सर उसमें से अपन ये क्या मालूम करे वो जरा एक्सप्लेन करना अपन एक एग्जांपल सॉल्व करें ना सर
क्या
ये प्रॉब्लम सर कर्ल और डाइवर्जेंस एक प्रॉब्लम करें ना सर अपन
प्रॉब्लम्स तो प्रॉब्लम ही होता है, वहां से आपको क्या कंक्लूजन्स मिलेगा क्वेश्चन.
हाँ सर अब ये डाइवर्जेंस अपने को एक आया ना सर स्पेस के ये क्वांटिटी लाइक डेल डॉट एफ इज इक्वल टू k1y प्लस 6xz. हाँ सर हेलो सर
I can hear you. Proceed.
डेल डॉट एफ इज इक्वल टू k1y प्लस 6xz. तो अब ये इससे अपन उसको नेचर को बाय सीइंग दिस कैन वी डिफाइन दैट नेचर सर आई मीन यू हैव दैट सेकंड स्टेटमेंट यू हैव सेड ना सर दिस इज द डाइवर्जेंस ऑफ द फील्ड.
आप क्या बोल सकते हो, आप वहां पर वो पॉइंट के पास उसका नेट फ्लो है -6, ऐसा बोल सकते हैं.
Okay. Okay, net flow -6. Yeah. Then again the curl also वहाँ पे rotation that value बोल के बोल सकते हैं क्या सर?
आपको ऐसा है 4x क्या वेक्टर है ना, आप ऐसा बोल सकते हैं कि x डायरेक्शन में रोटेट हो.
डायरेक्शन में मैग्नीट्यूड के साथ रोटेशन हो रहा हो गया सर. एक बार वो कर्ल ये कर्ल का एग्जांपल निकालो ना कर्ल का एग्जांपल. हाँ ये नहीं एक नॉन जीरो कर लिया
नॉन जीरो का नहीं दिया था.
अगर कर्ल का आंसर कर्ल ऑफ ए वेक्टर इज इक्वल्स टू 6x कैप माइनस 7y कैप बोल के आया सर, तो अपन उससे क्या इन्फर कर सकते सर? 6x कैप माइनस 7y कैप फॉर एग्जांपल. हाँ सर
यहाँ पर 6 यूनिट्स है, 1 2 3 5 6, 1 2 4 5 6 7, यहाँ पर ऐसा वेक्टर रहेगा. इसका मतलब है इस ऐसा बोल सकते हैं. उसका मोमेंट उतना, उसका रोटेशन वो डायरेक्शन में आए, ऑब्जेक्ट का रोटेशन.
अगर वहाँ पर तो उसका रोटेशन और मिनट वो रहता बोल के.
हाँ
सर डायरेक्शन मतलब यूनिट वेक्टर 6 7 है ना सर?
हाँ
डायरेक्शन का रोटेशन डायरेक्शन का रोटेशन अपन फाइंड कर देना सर. वो 6x कैप प्लस 7y का यूनिट
यूनिट
सर. सर एक्चुअली वॉइस पूरा कट हो जा रहा है सर, क्लैरिटी नहीं आ रहा.
हाँ वो डायरेक्शन में वो रोटेट हो रहा है, ऐसा आप इंटरप्रेट कर सकते हैं.
Okay, sir. Thank you, sir.
और अब हम बाद में भी इस्तेमाल करेंगे कर्ल और डाइवर्जेंस को, और दूसरा
हाँ सर. हाँ सर. Thank you, sir.
लगातार हम इस्तेमाल करेंगे पूरा हमारा सब्जेक्ट है, वहां पर
जी.
फुल क्रैक आ जाएगा.
जी
So,
सर.
any more questions? You can ask me in Hindi and Telugu also. I'm comfortable with those languages as well, as far as doubt clearing session is concerned. Any more questions? Okay, then I'm going to close the session. Good night.